And welcome to today's video, Falling Objects. As you can guess, this video is going to be about objects that fall, but specifically it's about objects that fall to the Earth, most likely within the atmosphere. So near the surface of the Earth, all objects experience about the same acceleration due to gravity. And you should all know this by now, that the acceleration due to gravity is negative 9.8 meters per second squared. So for every second that something falls, its velocity increases by 9.8 meters per second. And a falling object is one of the most common examples of motion with a constant acceleration. You can also talk about a car moving with a constant acceleration, but it's more likely that that car is not moving at a constant acceleration. It's hard to get the acceleration of a car to be exactly constant the whole time. But if you drop something on Earth, it naturally moves with a constant acceleration. All of the objects on Earth will fall at 9.8 meters per second squared with that acceleration, as long as we don't take into account air resistance. It's kind of hard to ignore air resistance, especially if you're looking at things like a baseball versus a sheet of paper, because the baseball is more compact. It has less surface area, so air resistance doesn't affect it as much. But a sheet of paper laid flat will have a lot of air resistance because it has a wide area. However, if we crumple that piece of paper up, the mass is still the same, and it's still less than the baseball, but now its surface area is comparable to the baseball, and so we have reduced air resistance. So in B here, we can say this is more like what would happen when there's no air resistance. Both objects will fall with the same acceleration. So what are we saying about an object's mass? Well, we're saying the mass of an object does not determine how fast it will fall. No matter what the object is, it always falls with an acceleration of negative 9.8 meters per second squared, as long as we ignore air resistance. So here's a little video from Rosencrantz and Guildenstern are Dead, and it's about this principle.
Look at this. Leaving, sir. This is interesting. You would think this would fall faster than this, wouldn't you? And you'd be absolutely right.
So in this video, Rosencrantz is throwing things back into the bin where they belong and discovers that two objects with different masses hit the bottom of the bin at the same exact time. But that's kind of counterintuitive to him because he thinks, oh, the heavier thing should fall faster. It should hit first. And so he tries to demonstrate with a feather and a small steel ball, and what happened there? Air resistance got in the way. The air resistance acted more effectively on the feather than it did on the ball. So the air resistance was counteracting the acceleration due to gravity and made it fall slower. However, the acceleration due to gravity on those objects was still the same. It's just that the feather had more of a force due to air resistance balancing it out. So the acceleration due to gravity at the Earth's surface is approximately 9.8 meters per second squared, and we know this. If you do not know this, you need to write this down somewhere, make a star next to it, because this is going to be super, super important for the rest of the year. So if we look at the Tower of Pisa up here, let's say somebody drops a ball from the very top. They don't throw it down, they just let go of it, so its initial velocity is 0. After 1 second, the ball will have a velocity of 9.8 meters per second because it has an acceleration of 9.8 meters per second squared. If we do the math using one of our equations, we find that after 1 second it has fallen 4.9 meters. After the second it has fallen 1.9 meters, or 19.6 meters, sorry. And it is going 9.8 meters per second times 2, because it has been 2 seconds. And after the third second, it has fallen 44.1 meters, and it is going a speed of 9.8 times 3, because this is after the third second. So each second that something falls, we add 9.8 meters per second to its initial velocity. And it will fall farther and farther each time. So let's do an example. The observation deck of a tall skyscraper is 370 meters above the street. Determine the time required for a penny to free fall from the deck to the street below. So this is just like any of our other constant acceleration problems. The first thing we want to do is draw a picture. So we have a skyscraper, and there is a penny that is falling from the top down to the street below. Our skyscraper is 370 meters tall, and if a penny is free falling, we can assume its initial velocity is 0. Somebody didn't throw it down or throw it up first, they just let go of it. So now let's list everything we know. We can have up to 6 different variables: the final velocity, initial velocity, acceleration, time, initial position, and final position. Do we know how fast the penny is going when it hits the ground? Not really. We could figure it out, but we are not given that in the problem, and we can't assume anything about that. But we do know how fast it starts. In the beginning of the problem, it's dropped, so it has an initial velocity of 0. Its acceleration is negative 9.8 meters per second squared. This penny is going to fall to the ground because of gravity. And anytime you have something falling or changing direction due to gravity, it always, always, always has an acceleration of negative 9.8 meters per second squared. We do not know the time it takes for this penny to fall. This is what we're trying to find. Determine the time. Its initial position we can call 370 meters because it's starting at the top of the building. And if we call the initial position 370, the final position needs to be 0. So the one thing that we do not know out of all of these variables and don't really care about is final velocity. So we need an equation that does not have final velocity in it. And that is our very first equation. The change in position is equal to initial velocity times time plus 1/2 acceleration times time squared. And now all we have to do is plug in our numbers. Our change in position is right here. It starts at 370 and goes to 0. So its change in position, which is final position minus initial, is going to be negative 370 meters. It fell from 370 to 0, so its displacement was negative. So negative 370 meters equals 0 meters per second times t plus 1/2 negative 9.8 meters per second squared times t squared. So we have negative 370 meters over here, and this side simplifies to negative 4.9 meters per second squared times t squared. And it's negative 4.9 because I multiplied negative 9.8 times 1/2. So now I need to grab my calculator and we can solve for t. The first thing we're going to do is divide both sides by negative 4.9 so that it cancels here and we get t squared by itself. So negative 370 divided by negative 4.9 is 75.5. And that's equal to t squared. And now to solve for t, we need to take the square root of both sides. So the square root of 75.5 is 8.69 equals t. And what do we measure time in? Seconds. So we have a really tall building here. We have a 370-meter building. That's about 1,000 feet. And it will only take the penny a little over 8.5 seconds to fall that entire distance. So your homework for tonight is to describe the motion of this ball. So there is a ball, which is the circle here, and it's thrown upward. Describe its acceleration, velocity, and displacement as positive, negative, or zero at each indicated point. So a suggestion to you is to draw this picture and label each of these. So I would label this as number 1, 2, 3, 4, 5, and then make a chart. So for 1, 2, 3, 4, and 5 is its velocity, acceleration, and displacement, positive, negative, or zero. So you make a graph like that and fill in everything with a positive, negative, or zero. So do your best on this and have it ready to hand in the next time that you're in class.